My name is Jacob Dayan, and I'm going to talk about the first laboratory from Physics 2211 that talks about constant velocity and Newton's second law. Okay, so first of all, I'm going to talk about the introduction of the laboratory and how Newton's second law applies to it. Then I'm going to explain and define the analysis of a ball's motion, and then do a computational model of the real-life situation, and then compare both models, the real-life and the computational model. And then I'm just going to answer some follow-up questions from the laboratory. Well, Newton's second law defines how a system interacts with its surroundings when an external force from outside causes a change in momentum of the system in relation to its mass, time, and velocity. Additionally, we can observe from the formulas from below that when there's no net force acting on the system, when the net force equals zero, its acceleration and change in momentum are zero, which basically means that the object remains moving in constant velocity. As we know, delta P, the change in momentum, equals net force times delta T, which can just be derived into the velocity update formula. That if we divide that formula by its mass, we get that final velocity equals initial velocity plus net force times delta T over its mass. When the net force is zero, we just get that the final velocity equals the initial velocity. So the experiment plan is basically to record the motion of a ball moving in a straight line at constant speed. Then I'm going to import the video into Tracker and catch the object position during several time intervals and calculate its constant velocity. Then I'm going to use the GlowScript coding system to create a computational model of the object's motion, and then I'm going to sketch a time versus position graph using the collected data from both experiments. And then I'm going to compare both the real life and the computational models. Well, for the first experiment, I decided to roll a ping pong ball and track its movement during a certain time interval, assuming that there was no air resistance or friction. Then I tracked the ball movement after it left my hand, making sure that there was no external force acting on it, avoiding any acceleration, resulting in constant velocity for the ball. As you can see, I used the Tracker program to track the ball time and position in different time intervals. As you can see, the position changes very slightly, so that's why it's not shown very much in the graph. As you can see, the initial position and the initial time just gives us the initial velocity for the ball. So now in the computational model, I basically edited the code to display a situation very similar to the one we just demonstrated earlier. As you can see, the initial position and the initial velocity were the same as the ones used in the original model, as you can see in the picture from the GlowScript Python model. Also, as we know, that the mass does not affect the object velocity as the net force equals zero. Moreover, I used the position and velocity update formula to track the ball's motion in the computational model. Now I basically just compared the real life and the computational model into a position versus time graph to show that both models were basically very similar. The reason why it's a negative slope is because I used the negative x-axis since the ball was moving to the left. As you can see, both models were very similar, which means that the computational model gave an excellent representation of the real-life experiment. To conclude, I'm going to answer some follow-up questions of the experiment. First of all, what if the x-axis were flipped? The only thing that would have changed is the position of the ball. More specifically, its sign. If the ball was moving to the right, it will be shown as moving to the left or vice versa at the same time intervals, meaning that time and velocity will not change, only its sign. Second of all, can we know exactly how many pushes or pulls or forces were added together to give the system a zero net force with constant velocity? The answer to that is no. We cannot know because it is impossible to calculate the friction, the gravity, the air resistance, or any other force that was acting upon the ball by a single observation as we did in this experiment. Well, that's it for today. Thank you very much for your time. And this is it for me, Jacob Dayan, and Physics 1 first experiment. Thank you very much.